Homomorphism. So homomorphism is a combination of the homo, which means same, and morph, which means shape. So it is a map between two mathematical structures that preserves the structure. So meaning, it is a way to compare two groups for structural similarities. It's a function between two groups which preserves the group structure in each group. So if two groups are homomorphic, it doesn't mean they are the same. It just means they are similar. Additionally, not every pair of groups will have a non-trivial homomorphism between them. Some groups are so different from one another that there are no structural similarities at all. To better understand this, suppose we have two groups G and H. Note that G and H are different groups and they may have entirely different group operations. To help us keep G and H separate in our minds, let's use the asterisk for the group operation in G and the diamond for the group operation in H. Now, pick any two elements x and y in G. Let's say that x times y equals z. Next, suppose we have a function that maps G to H. The three elements x, y, and z are mapped to elements in H. X is mapped to f of x, y is mapped to f of y, and z is mapped to f of z. The whole point of homomorphism is to find a structural similarity between two groups. So if x times y equals z in G, then we'd like f of x times f of y to be equal to f of z in a group H. So f of x times f of y equals f of z. But z equals x times y. Substituting this gives us f of x times f of y is equal to f of x times y. So this is the definition of homomorphism. Example, let G be the group of real numbers under addition and H be the positive real numbers under multiplication. G is an abelian group with identity element of 0 and H is an abelian group with identity element of 1. Here's the homomorphism. Define the function f that maps x to e to the x. To make sure this is a homomorphism, we need to verify that f of x plus y is equal to f of x times f of y. Don't forget that the group operation for G is addition. So while the group operation for H is multiplication. By the definition of f, this says that e to the x plus y equals e to the x times e to the y. And this is true. This is one of the rules of exponents. So, f is a homomorphism. Another example. So, G will be the real numbers under addition and will be a complex numbers with absolute value of 1. These complex numbers form a group under multiplication. So, define the function f as f of x equals e to the I times x. For f to be homomorphism, we must have f of x plus y equals f of x times f of y. So this is true only if e to the I times x plus y equals e to the I times x times e to the I times y. So we can see this is true by expanding the left-hand side. Then, using the rules of exponent, it's true. So f is a homomorphism.
Now, we will discuss about isomorphism, presented by Juna Mae Apolinario, BSed Math 3B. So, isomorphism derives from the Greek words iso, which means equal, and morphosis, which means to form or to shape. Suppose we have two groups G and H and a homomorphism f from G to H. Recall that a homomorphism is a function f such that f of x times y is equal to f of x times f of y. Now, a homomorphism does not have to be one-to-one or injective, or where every element in the codomain H is mapped by at most one element from the domain G. Similarly, f does not have to be onto or surjective, or where element of codomain H is mapped by some element of the domain G, and it ensures that the entire codomain H is covered by the function. But for the group of G and H to be identical, we need a homomorphism f to be one-to-one and onto. F needs to be both an injective and surjective. This way, we can pair each element in G with a unique element in H and vice versa. Thus, this is a definition of isomorphism. So, isomorphism is a homomorphism that is both injective or one-to-one and surjective, which is onto function. For our first example, consider the groups of the positive real numbers under multiplication and all real numbers under addition. One homomorphism between them is a logarithmic function. We can check that this is a homomorphism by using the laws of logarithms. The log of x times y is equal to the log of x plus log of y. To see if this is an isomorphism, we have to test if it is a bijection. Let's check first that this function is one-to-one. Suppose that log of x is equal to log of y. Since the logs are equal, e to each power is equal to. This simplifies to x equals y. So, this function is one-to-one. Next, the range of the logarithmic function are all real numbers. So, this function is onto. So, in this example, the logarithmic function is a homomorphism and a bijection that makes it an isomorphism. Thus, these two groups are isomorphic. Our second example is about isomorphism of graphs. We need to consider first the properties to tell if a graph is isomorphic. First, the two graphs A and B should have the same number of vertices. Next, the same number of edges, the same degrees of vertices, and the same cycle length. So we will start with the graph A. So the number of vertices is 1, 2, 3, 4, 5, 6. For graph B, 1, 2, 3, 4, 5, 6. For the number of edges, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. For the degrees of vertices, we have 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. For the cycle length, we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Since all properties are satisfied, thus the two graphs A and B are isomorphic.
Automorphism. By the way, I am Juna Rivera of BSN Math 3D. So first, we define what is automorphism. So automorphism comes from the Greek word auto means itself and morph means shape. So a shape morphs to itself. So first we let G be a group. An automorphism of G is an isomorphism of a P when group G maps to itself or G maps to G. The set of all automorphism of G with the operation of a function composition first of a group denoted by odd G is an automorphism. So, not all automorphism of a group arrive in this way, as we defined earlier, but we can also say some of its properties as the identity of a function is an automorphism. Next is the inverse of a function of an automorphism is an automorphism. Third one is the composition of the two functions, as we have here as the phi and the c of an automorphism is an automorphism. Example number 1. What are automorphism and integers with a mod 6? So first we illustrate the generators of mod 6 maps to C mod 6. So the generator integers mod 6 is 1 and 5. So by identity property, we can say that when the function of maps of 1 is also maps to 1. So it maps to itself from here 1 to 1. Same goes with 2 maps to 2, 3 maps to 3, 4 maps to 4, and 5 maps to 5, 0 maps to 0. That's it. That's it by identity property. And we can say that a function
function of x is equal to x. But we can also prove an automorphism of integer policies in another way. So we can get from the generators, which is 1 and 5. So when we maps 1 to 5, we are just only adding 1 here. So we add 1, so it becomes 2. Then we subtract 1 on the other side. So we can have 4. So then add 1. Then we can have, we subtract 1. Then we have 3 maps to 3. As well as we add 1 here, we have 4. Then we subtract 3 by 1. So we can have 2. And then we have to add 1 to 4. So we have 5. Then here we have the 2 minus 1. So we have 1. So 5 maps to 1. And then lastly, since it's mod 6, so we have to 0 also maps to 0. And with that, we can say that the function of x is equal to negative x. As we had just only add 1 here, and the other side we have 1. Example number 2. Given an odd G is a subset of a certain group G, show that for all f sub 1, and f sub 2 is also an element of odd G, where odd G is equal to f is an element of a certain group G, such that for all G sub 1, G sub 2 is an element of G, and f of G sub 1 and G sub 2 is equal to f of G sub 1 and multiplied to f of G sub 2. So to show, we have f sub 1 composition of f sub 1 and f sub 2 is an element of odd G. That we just first expand the composition of f sub 1 and f sub 2. So we have f sub 1 multiplied to the quantity of f sub 2 times the quantity of g sub 1 times g sub 2 is equal to f sub 1 multiplied to the quantity of f sub 2 of g sub 1 times f sub 1 times the quantity of f sub 2 of g sub 2. So first, we just only going to find the easier function to compose. So we go with the left side here. So we expand it. So we have f sub 1 multiplied to the quantity of f sub 2 of g sub 1 times the quantity of f sub 2 of g sub 2. F sub 1 multiplied to the quantity of f sub 2 of g sub 1 times the quantity of f sub 1 times the quantity of f sub 2 of g sub 2. So to further expand our left side, since it's the only one we're going to manipulate, and the right side we're going to stay. So we have f sub 1 multiplied to f sub 2 of g sub 1 times f sub 1 multiplied to the quantity of f sub 2 of g sub 2 is equal to f sub 1 multiplied to the quantity of f sub 2 of g sub 1 times f sub 1 multiplied to the quantity of f sub 2 times g sub 2. So by composition of the function, we can therefore say that for all f sub 1 and f sub 2 is an element of odd G is true. So I hope that you already understand what is homomorphism, isomorphism, and automorphism. So on your own, just try the following.